All right, line Q1, learning task number 3. We're going to be working on determining some of our conductor requirements. We've talked about determining our cables in the previous one. We identified, the materials that we use, why we use materials in the first learning task. We identified the types of cables that we have, why we use them, the different voltage ratings, the type of plastic we use, and things like that. So the second one, now what we're going to do is we're going to start determining our conductor requirements that we are going to go and utilize. This one is going to be a long set of code, and it is going to all be heavily code intensive that we are going to need to do this. So let's talk in, see what we get done here. All right, I'm going to move that one out of the way. We'll get the picture of a fish tape later on. It's not blowing your minds anyways. You've all seen these before. Let's start with the very first where they talk about Ampasities. We do know Ohm's law and we know how to calculate amps. If I have got amps that are calculated, I need to be able to now go and pick a conductor that is going to be good for that. Let's go with the example that they're giving us where they say we have got a device that requires 48 amps of current that's going to go through. What we'll need to do is we are going to go into our Canadian electrical code and we are going to go down to our table number 2 if we're working with copper. If we're working with aluminum, we will be identified as working with aluminum. If there is ever a question that does not have the material type listed, you are going to need to say it is copper. This is just the default. It's the expectation of you on the standard level exams, on your interprovincial, that if it is not listed, it is copper. The circuit is going to require how many wires? Well, obviously, it needs to go and have 2. Otherwise, we would not have a circuit, right? If we take a look at it, if we're going to bring out 48 amps, we would also need to go and bring back 48 amps as well. So that's what forms an electrical circuit, which means that we got a minimum of 2 wires anytime that we're looking at a complete circuit. If we go back into our Canadian electrical code over here, we see that table 2 deals with not more than 3 conductors inside of a raceway or inside of a cable. So this is inside of a overall thing that's holding it together. It could be a raceway or cable. If I compare that to my table number 1 is for single conductors, unshielded and in free air. So it is not that we're going to be looking at. It's very rare that we're going to deal with those unless we're working in certain high voltage industrial applications. Most of what we're going to do is kind of come out of this one here, not more than 3 insulated conductors. What we're looking for is we are looking for a conductor that can carry at least 48 amps. Well, we see that 48 amps, I could carry that here, I could carry that here, or I could carry it here. It's really going to depend upon the temperature that we need to go and carry that at. If they give you a temperature, we use the temperature that is going to be given. For these, if they say it's a 75 degree, the easy lookup for that one is just going to be find your 75 degree column, carry that thing down, track across till you hit that 50. It's bigger than the 48 amps that we need, so we're good to go. A conductor can always carry 100% of the current that is associated with it. Every single time. There's going to be some demanding on our demand loads that we will have for equipment. We'll cover those when we get there. But for conductors, if that conductor is rated for 50 amps, it could carry 50 amps all day, all week, all month, all year, all millennia. It is going to be perfectly fine operating fully loaded if it's a conductor. We do sometimes have to go and derate conductors, particularly when we have got more things that are going to be at play at the same time. I'm just going to go down to my derating tables over here, which are going to be my table 5. A couple of deration tables that we have. One of them is going to be for ambient temperature rises. Now, tables 1 through 4 are dealing with up to 30 degrees. 30 degrees for indoor wiring is pretty normal. But by the time you go into an attic, or if you go into a boiler room, those areas can be well over top of 30 degrees. And if I am over top of 30 degrees, I do need to go and derate the amount that I can carry through my conductor because of that extra heat. Remember that my resistance is going to be affected by heat. All of our copper, aluminum stuff have positive temperature coefficients. It means they get more resistive with heat. So if I take that conductor that I was looking at before, that we said, look, we could take it number 8, AWG, to carry 48 amps. That was fine when it was up to 30 degrees. How much amps could that 50 amp conductor, the number 8, carry at 35 degrees? Well, we would have to go and use this multiplier. I'm just going to pull up a calculator here. We'd use this multiplier of 0.94 right over there, and the actual ampacity. So that wire was rated for 50 amps times 0.94, which tells me that, I can only carry 47 amps. So I could not be using that number 8 if it was over 30 degrees. If it was, between 30 to 35 degrees, would not be able to go and utilize that one that we had there before. Let's just go back up to it and we'll take a look one more time. So here's my conductor size. We said we needed to carry 48 amps out of the 75 degree wire. We picked this one over here. We said number 8 is good. It's good for 50 amps. But when we tried to derate that for a higher temperature, it didn't work. We would have to grab the next size otherwise. Our other derating factors that we are going to have are going to be based upon the number of conductors. Now, this table 5B is a deration that I can only use on tables 1 and 3. I'm allowed to derate my single conductors. How often do we do that? Hardly ever, so let's skip past that one. Let's take a look at table 5C over here. 5C is ampacity correction factors for tables 2 and 4. Highlight at tables 2 and 4 inside of your codebook. This tells about the insulated number of conductors that we are going to have. So if I have got more than 4 or more than 3 conductors, I'm going to have to derate. In other words, I can take my value, that 50 amps that we had for number 8, and it is good for anywhere from 1 to 3 conductors. I can run that amount of current through there. It's 100% correction. However, if I have got 4 to 6, let's say it was inside of a conduit, now I would have to derate it down to 80%. So if I take my 50 amps times 0.8, gets me down to that 50 amp conductor would only be good for 40 amps if I'm going to have a whole pile of them that are going to be shoved together. There is something we need to know about this number of insulated conductors, and that is going to be that under 4004, which it references us to, we talk about the duration that we would have for a neutral. Take a look at subrule 3. This is 4004 subrule 3. It says a neutral conductor that carries only the unbalanced current from other conductors shall not be counted in determining ampasities as provided for in subrules 1 and 2. Highlight a neutral conductor and highlight shall not be counted in determining ampasities. Okay, just those two. When we're looking at these, if I have got a set of cables that have got some neutrals inside of them, I don't need to count the neutrals as part of my conductors for doing my durations. Same with, if I go down to number 6, a bonding conductor, highlight bonding conductor, and then shall not be counted in determining the ampacity. So I don't need to go and count the bond inside of there as well. Let's go back into what we have over here. So let's go take a look at a conduit, and we'll just stick a couple of conductors through it. We'll count up how many conductors we actually are carrying through it. So we're going to go and have 2 red conductors. We'll take 2 black conductors. We will take 2 green conductors, and we will take 2 gray conductors out of this thing. What do we know about a conductor is just based upon the number of conductors that I have here and the insulation? Well, you should be able to count this all up. We see that there's a grand total of 8 conductors in total inside of it. Of that 8 conductor, 2 of them are identified green. That green means that they would have to be identified as grounding or bonding. And what we just took a look at over there, the bonding conductor, we don't need to count those for determining ampacities. So in this case, we get to jump from 8, we're going to go down to 6 now. Then let's take a look through these. Reds are identified underneath my 4032, that those are going to be conductors. Same with blacks. What about gray? Well, we know that gray is what we use to identify a neutral. So I've got 2 neutrals that are going to be inside here, are identified conductors, properly speaking. Do I count those? Once again, going back into here, the neutral conductor does not get counted. So I get to go and drop those ones off as well. So I'm going to drop that down. Now we are going to be down to 4 conductors. The only conductors that I count for determining my ampasities in here, the duration, is going to be these 4 that we're going to have. Later on, once we get all into 3rd year in particular, we're going to see how the cancellation of current happens and why, the neutrals shouldn't count and why the bonds don't count, because they're not carrying any active current over top of them. But if I needed to go and derate for these, going back into that, I can go down to my table. I'm just going to go to table 5C. If I take a look at table 5C, I'm going to have to derate my conductors down to 80% because there is what we consider to be 4 active conductors inside of there. You would not want to be derating it down to 70%. Yes, there's 8 physical conductors, but 2 of those conductor types, neutrals and bonds, don't get counted for doing my durations inside of there. So this one, we would only need to derate our conductors down to that 80%. There's a couple of other times that we do need to also derate, based upon contact. This is where I've got them all inside of a, either a cable or inside of a conduit. That's easy to go and understand. But what about in cases like this? And you have all done this before, where you're wiring up a suite or something like that, and then the only place to bring your cables down is in from the top. And so you have all of these cables that are just being brought down and they're being stacked really close together, and you've got a couple of just scab pieces of lumber that are going to be behind that. The length that you bundle these cables together is going to go and determine whether or not you need to go and derate. We have to watch that length when we're bringing these things together, because if you go past that, and trust me, the inspectors know all about this and they will not hesitate to bust you on that. If you go past that, you're going to run yourself into issues where you have to start derating. We don't want to have to derate all of our lumixes, if at all possible. Let's go back into our Canadian Electrical Code over here, and we're going to go jump back down into my section 4 over here. And what we want to do is we want to just talk about conductors that are in contact with each other is what we're looking for. So we're just going to roll down through here, down through here, down through here. I know it's a lot of rolling to get through this all. Down through here, and stop on 13. So 14004. Where multi-conductor cables, that is a 14.2 lumix or any other type of lumix, is run in contact for distances greater than 600 millimeters, so more than 600 millimeters. 300 millimeters is a foot, that's 2 feet. The Ampasities shall be corrected by the correction factors from 5C. Highlight this and that alone. Don't highlight the whole rule. Okay? If you highlight the whole rule, it's really hard to pull the important parts out of the rule. A lot of my rules only have maybe 1 or 2 words highlighted inside of them, but it gets me to the important, the heart of the rule there. So in our installation over here, that 600 mil, if this is more than 600 mil or 2 feet that we're going to go and have, 600 millimeters, that's 2 M's there, then I would have to derate my cables. Don't be taking these things. If you got a 10-foot wall, you want to make sure you space these things. Do note the wording as well, that run in contact. If you have got a single cable diameter in between them, it does not count. So I can go, if I were to look at this, if I have got lumix, and I'm just going to take a cross section of my lumix over here. 1 lumix, 2 lumix, like that. As long as whatever this distance is, I've got the same equal distance between it and the next one, that all of these are equal, it does not count as being in contact. But as soon as I stack 2 of them underneath, like an S2 staple or any of those other things that we do to bring our cables together, it's allowable. Just do it only for short distances. All right, looking at what's inside of or going back into the binder, because I want to make sure I hit what we have inside of here as well. We've talked about those. We've talked about those. Yeah, they talk about a duration that you would need to have. They go through a bunch on examples 1, 2, and 3, where they work at derating the actual cables themselves. Go through those examples. It's the same things that we're doing over here inside the video, but it's just a layout where they're showing you what these each are happening, and they're giving us different, values that we're going to go and pull out. They're showing that we're going to, if we have derating, we are going to need to increase the size of our cable to make up for the capacity that we have lost inside of them. Conditions of use. We've already covered that one in the previous video where we took a look at table 19 and table 11, but conditions of use is just going to be talking about where I'm allowed to go and use certain types of conductors and cables based on the environment, whether something is dry or whether something is going to be damp. One of the big contentious components inside of there has always been lumix. When are you allowed to go and start rough wiring a house? Can you do it as soon as the walls are up? Are you allowed to be wiring before the roof is all the way on, etc.? You got to take a look. What is the condition of use for a lumix itself? Let's just go to that one. Where's my code? And we will roll down. Give me a sec here to just find that table 19. And I'm going to go and look for any place where I'm going to go and see my NMD. It's for exposed wiring in dry locations. Okay, that's one spot where it's showing. It's for exposed wiring in dry or damp locations. So I can use it in dry locations. I can also use it inside of damp locations. Can I use it inside of a wet location? Absolutely not. And if I go through these ones just a little bit further, there's NMWUs and things like that, but those aren't NMDs. And I can go through, there's another NMD over here, but that one is going to be associated with concealed wiring in dry or damp locations, so inside of walls. But once again, it is dry or damp that we are going to be limiting ourselves to. Just roll through a little bit further over here, make sure we've got all of them. So anytime you're doing a lookup like this, go through the whole code. Okay, we're going to go through that whole table there. And no NMDs off of that one. I'm sorry, I'm talking weird because I'm sticking my head sideways so I can read my code tables over here, but c'est la vie. And nothing there. And NMDH, that's a new type of one, but that's different than what we're doing here. It's a exposed type of Lumex. It's a hardened one or whatever. But okay, nothing else that's inside of there. So I know that NMD can be used inside of a dry or damp location. Let's talk about wood frame construction. When is it dry? Well, obviously when it cannot be rained on, right? You know, plumbers having a rupture pipe or something like that, that's outside of what the code allows for. That's accidental. But, you know, rain, that's something that absolutely would go and happen. So what determines whether something is going to be dry or damp? To do something like that, we need to go into some of our early sections of our code, specifically section 0, that's going to go and talk about dry versus damp and other types of locations. And what we're going to do is we're going to go all the way down until we find location. Oh, there we are. And then that is going to go and give us what's a dry location, what is a damp location. So check this out. Dry location is a location not normally subject to dampness, but that may include a location subject to temporary dampness. Note that they say dampness over here in the case of building under construction, provided that ventilation is adequate to prevent an accumulation of moisture. So a dry location, we count a building that's under construction as being a dry location. Yeah, it's damp inside of there. There still might be some puddles kicking around and stuff like that, but it's not going to be an actual wet location. Damp location is condensation of moisture and includes partially protected locations underneath canopies, marquees, roofed, open porches, and similar locations. So do these work for us inside of construction? Well, we would have to say dry or damp is fine. We see that, you know, we should fit those. When is wet? Anytime that a liquid may drip, splash, or flow on or against electrical equipment. A wet location would be us wiring before the roof is on. Once the roof is on, we can start doing our wiring. Usually we wait for doors and windows, but that's just because we don't want to have all of our wiring stripped out by bicycle bandits. But we don't have to wait for anything more than the point that there's no longer water that is going to be dripping, splashing, or flowing up against our equipment. All directly out of our Canadian Electrical Code. Okay, conduit fill. Couple of different ways that conduit can be filled, or the way that we can go and choose fill. There is the easy cheesy method, and then there is going to be the longhand method. Both of them have their places inside of our industry. Let's start by taking a look at our easy cheesy method, and before we even do that, let's start by taking a look at the rule that is going to go and talk to us about conduit fill. Where are we going to find rules for conduit fill? Well, first we have to say, what are we doing when we're putting stuff into conduit? We're doing installation, which means that we should be looking at our installation rules to do with conductors and things like that. Section 4 deals with just the conductors itself. Talks about, defines what a conductor is and how we use it and where we place it. Section 12 talks about how we use this as wiring itself. So section 12 is where we're going to want to kick into, and then 12 is going to go and be broken down into a number of different things. We're going to start with a scope. Every section always starts with a scope, tells what that thing is going to go and cover. Then we're going to go and have general requirements. We are also going to go and have conductors rules. So it's going to be rules that are going to be talking now about the installation of conductors. some general rules on insulated conductors and cables, and then we're going to start going into individual ones based upon the types of wiring that we might be doing. You know, open wiring, exposed wiring, flexible cables, all of these things are going to be placed inside of the section 12 in their own headings that we are going to look at. Let's take a look at raceways. Now, there are going to be general rules for raceways partway through. If we go all the way down to 12,900, so the first section deals with all the cables of section 12. The second section deals with all the raceways. And this talks about, you know, the general section that's going to apply to all raceways, and then we will fine-tune that into other ones. Conductors inside of a raceway starts inside of 12,904, so this is just going to go and talk about how I'm going to place them in. We do need to make sure that there's going to be room inside of each one, etc. We have to talk about how we protect them, where they come out, placing bushings or other things on there. We talk about inserting them in there. You know, how we make sure that we're not going to burn the insulation in our pull. Everybody's seen that before, damaged insulation from a pull. You know, we should be putting wire lube onto it. You're not allowed to be using cleaning agents, soap, or other types of, you know, lubricants. It has to be the only stuff that's going to be approved. You can only go and use actual pulling compounds, or pulling compound, talc, or soapstone. You can use some powdered dry mineral as well. But down here is what we're looking for. 12,910, conductors and cables in conduit and tubing. First rule says the conduit tubing has to be sufficiently sized to permit the conductors to be drawn in and withdrawn, taken out, without damage to the conductors or to the conductor insulation itself. And then sub-rules 3, 4, and 5 only apply to complete systems where it goes from box, raceway to another box, and not to short sections of conduit tubing used for the protection of open wiring. So sometimes we will do what we refer to as sleeving. Everybody's seen that. You got a tech cable or ACW coming out of the ground, and you stick a big chunk of rigid PVC around it so that when the homeowner is running the whippersnipper, they're not going to end up cutting through the exterior jacket, right? That's what this rule is talking about. We don't have to worry about those short little chunks that we're using as sleeves. We're talking about complete stuff going from box, using a raceway to another box. Sub-rule 3 over here talks about the maximum number of conductors cannot go and exceed 200. And then sub-rule 4 talks about our fill. Now mine's got a little E next to it, and that's because there was a little bit of errata or small error. In the early ones over there, it was just they forgot to put, I think the last 9, they ended at 9K or something like that. Whatever it wasn't anything major inside of there. But it said the maximum number of conductors or cables inside of a conduit shall be such that they do not result in a greater fill than that specified by Table 8. Stop right there. So the first thing that this rule says at the very top, and I know we want to read these ones, don't do it, but the first thing it says is we cannot fill to more than what Table 8 tells us to go and fill. So let's go to Table 8 first. Table 8 over here says the maximum allowable % conduit and tubing fill. It says, how many conductors are we using? First of all, lead sheath conductor or multi-conductor cables. They're talking about not just multi-conductor, but lead sheathed multi-conductor cables. How many cables can I go and place inside of there? We're not going to worry because we don't deal with lead. This is what we're going to be dealing with is regular conductors and regular cables. So if I've got one cable inside of a conduit, it can fill 53% of the area. If I've got 2, they can only fill 31% of the area. And if I've got 3 or more, can only fill 40%. This 31% is a little bit trippy on the 2, but that's just because you'd have to think about the size that thing would be. 2 conductors, side by side would be half the diameter, and then you can go and do the math off of that one. Mathematically, it works out so that it's going to be less friction inside of there. It's just kind of a trippy number to have in the middle because it goes from high to low to kind of mid-range. This is a number we're going to memorize now. 40% fill. How full do we fill our conduit? That's right. I just heard you say 40%. And you will be able to say 40% on every, single question that you're going to run into that we do not fill. If we have got, anytime we got 3 conductors or more, we don't go more than 40% full. Okay. So that was the first part of our rule over there, where it said that, the maximum shall not result in a greater fill than that specified by Table 8. 40% is where we're going to say that it's going to be. Then it tells us that, look, the interior area of different types of conduit tubings shall be specified in tables 9A to 9P. So we're going to go and see a bunch of different cross-section, rigid metal conduit, flexible metal conduit. They're all going to have different internal sizes. Even though the nominal conduit size, that we might be looking at, 16 mils, 12 mils, things like that, this is going to be my half-inch conduit. Even though it's a half-inch conduit, we're going to give them different internal cross-sectional areas. The reason they get in different internal cross-sectional areas is the type of material they're made out of. Look at rigid metal conduit. That is made out of thick, heavy metal. It will be really good at dissipating heat, which means that if I take a look at the area, they're giving me an internal diameter of 1605. I'm going to go down here, take a look at PVC. PVC, they're giving me less area inside of there, less usable space, because PVC is plastic and it insulates and holds in the heat. We don't want to do that. That would heat stuff up. Basically, if you're ever wondering why we've got these different sizes, it's all to do with this whole concept of heat sinking, where any type of material that we are going to use for our conduits, the better that that material is at carrying heat away from the outside of the conduit. Let's take a look at this conduit that we have right down here. The better that this conduit is at taking heat and carrying it away from the conduit, the more we can fill that conduit up, because it's going to be able to keep the conductors cool. If I would replace the PVC, that PVC conduit would hold that heat inside there and would damage my conductors. Okay. Let's go and take a look back at that rule over there, because we're not done the analysis of the rule, but 12, 9, 10, we said that cross-sectional areas, we're going to take it to tables 9. That being said, it says, notwithstanding item A, the interior cross-section shall be permitted to derive from the measured internal or from the manufacturer's listed specification. So this is what we use as a general speaking, but we are also allowed to go and measure them ourselves if we want. Sometimes you could get a win off of it. Might be worth it. Usually it's just not worth the time though. Last of all, the diameters of cross-sectional areas of single conductor bare and insulated conductors shall be obtained by measurements. So we're supposed to measure each conductor. You guys all have calipers, I'm hoping? No, absolutely you don't have calipers. We don't do that. It says, notwithstanding item C, that's this section over here, the dimension of single conductor shall be permitted to be obtained from tables 10A to 10D for the constructions identified in those tables. So you don't have to measure. It's saying you should measure, but you are allowed to just go to your tables over here and then take your area out of those. Okay. Let's go and give ourselves a calculation. Two different ways that we can do the calculation. One is where we do all of this stuff over here. The other one that we're allowed to do is we are allowed to just use tables 6A to 6K for a single insulated conductors of the appropriate construction. So let's just talk about the easy cheesy table. 6A to 6K talks about maximum number of thermoset plastic insulated conductors with the jacket types R90, RW90 in one size of conduit. In other words, all of these have the exact same gauge and the exact same jacket. So if I had a bunch of number 12, if I was only running number 12s, I could stick 3 of them inside of a 1/2-inch conduit. That's a 16 mil. Or if I have number 12s, I could go and stick 16 of them inside of a 27. That's going to be a 1-inch conduit that I would have over there. That's great when I know what all my wire sizes are. But the problem is when I've got 2 10s and 3 12s and 4 14s, how do I size that? I cannot use these when I'm sizing multiple conductors inside of a conduit. Anytime that I'm going to be doing multiple conductors, I'm going to have to be using my tables 10 in order to go and do that. They give you some examples inside of there. Example number 5 is going to go and give you a set of conductors where you're going to have to go and pick out the size for each one. Then you're going to have to go and make sure that your fill is not going to be more than 40% fill with all those conductors and find out a conduit size from that. Example number 4 would allow you to go and take a look at your 6 tables, right? Because it's all one size. Your example number 4 inside of the book talks about 8 number 12s. So you could use those table 6s and find the correct type of conduit and take a look inside of there. And so, yeah, that's easy enough to go and do. Or for the other way, you could also still calculate those things longhand. So they do give you a longhand one that you could go and do as well. Either way, when they're all the same size, use either one. If I'm in a rush, I'll use these ones. If, however, I take the time and hand calculate it using these 4 over here, take my conduit area, take my conductor area, add them all together, make sure that I don't go over 40% fill. There's actually, some fairly substantial wins you can go and get. People might question, hey, isn't that overfull in a conduit? And you'd be surprised the number of times where you're not actually overfull where you are using, when you actually do the longhand calculation. Code is designed to be gamed by those that know. If you know, you can get away with a lot more legally than people that don't know. They've never put the time in to figure out what the code allows them to go and do. All right, voltage rating. Do finish those examples that are inside of there. Voltage rating, there's going to be different voltage ratings associated with different types of cables. We went over that inside of your table D1. If I don't know how many volts I can have on a piece of cable, I'm going to check it inside of table D1. Now, normally, I don't go to D1 first. Usually, I'm just going to look at a chunk of cable in my hand in front of me and say, hey, the jacket of this thing says no more than 300 volts, so I should probably not go more than 300 volts. Anytime that there's conflict between your D table and between the cable jacket always wins. The tables are designed as a general catch-all for anything that you don't have access to inside of the field. But usually you want to err on the side of first checking what is on the actual cable jacket itself. All right, voltage drop. Excuse me. Voltage drop is commonly going to be referred to as my IR drop. You'll hear it. People will say, the IR drop of this, etc. Anytime that we're dealing with a IR drop, we're talking about how much current amps am I putting through that conductor over top of the length of the conductor, which is acting like a big long resistance, and therefore how many volts am I losing before I get to my actual load at the far end. It can be a significant amount. Everybody's had that, where you're getting low volts on something because the cable run was just so incredibly long. If we go into our Canadian electrical code, it specs that we have got a maximum amount of voltage drop, excuse me, that is going to be based off of no more than 5% going all the way from my point of supply to where I use it. And of that, I can have no more than 3% in either the feeder or inside of the branch circuit. Feeder circuits are going to be things that feed to panels. Branch circuits go from the breaker in a panel to the other end. You can't have 3% in the feeder and 3% in the branch circuit. It's got to be an either-or type of situation, because if this is where my service entrance comes in, we'll just draw a little meter base over here, and we'll take that to a panel. And then we'll go from that panel, we'll take that thing over to a receptacle. Of these, this is going to be my feeder section. All of this going from here to the panel itself. This is going to be what we refer to as the branch circuit section. You can go and take a look at the definitions for circuit inside of the front of your electrical code book. They will give you all of those. If you go and take a look, it says that this terminates on an overcurrent device and final point of utilization. This cannot be more than 3%. This cannot be more than 3%. That's a maximum. But this from here to here cannot be more than 5%. In other words, if I'm going to drop 3% on the branch, that would mean that I could only drop 2% on the feeder. Or if I was going to go and drop the maximum on the feeder, 3%, then I could not drop more than 2% on the branch. You have to go and use both of those together to get you to the sum of not more than 5% that we are going to have. Table D3 is where we are going to go and find how to go and do our actual branch calculations for these. I'm just going to bring us down to my table D3, and there we are. And what it's going to talk about is distance to center of distribution for a 1% drop in voltage on a nominal 120 volt 2-conductor copper circuit. There is an example laid out, example number 7. Excuse me, dying over here. Example number 7 is going to go through how to utilize, excuse me, how to utilize that whole thing. I'm not going to go through example number 7. What I'm going to do is I'm going to go and link up to a separate video that does the voltage drop one. Read through the example 7, follow it along. Look for the mistakes that could be inside of that one. Make sure it lines up. Watch the other voltage drop video as well. Voltage drop is something that is expected that you know how to do. But every year when apprentices come back into school, they're always like, voltage drop. I hate voltage drop because it is not our easiest calculation we have in the code book. Watch the other video. Honestly, it's just going to be much more in-depth, and you should be able to hopefully do your voltage drops after that. We'll explain the DCF and everything else that's associated with that. All right. Let's talk about components here right now. when we're dealing with installing our conductors, this is where we finally get to go and take a look at all these pictures that we have over here. They introduce the concept of pulling. When I'm going to go and insert or withdraw anything into a conduit, we need to have some way to go and do so. Generally speaking, short runs, we're going to go and use a fish tape. If it's a long run, we are going to go and use a mouse or a bag or something like that. It's very common. People have, you should have all experienced this at some point, where you're going to go and have a conduit and you're going to bag the conduit, where you're going to go and have the conduit just goes underground from here to here. What you'll do is you'll attach a vacuum cleaner, just a shop vac. That's a terrible looking shop vac, but whatever. Attach the shop vac on so it's over top of that thing, so it's going to be pulling suction. And then what you're going to do is you're going to have just a bucket of twine, and then you're going to go and have a plastic bag. Most people just kind of like inflate a sandwich bag or something like that. You can also go and take, that white foam that they place underneath the sill plates at job sites. You'll find throwaway sections of that. If you roll that stuff up into a nice light little thing, make it a bit smaller than the size of your conduit, that stuff pulls through really, really nice as well. But you're going to go and have something attached to a string, and then you're just going to insert that in there, and the suction is going to pull that through. Always start first by cleaning the conduit out. First thing you should do if you're going to vacuum, all these shop vacs have the option to go and blow as well. Do not uncap a set of conduits and then pull it through your vacuum, because your vacuum has got this thing called the AC series motor that has brushes. If this conduit was glued together and capped, all of those fumes are still inside of it. And there are numerous people out there that have experienced vacuum cleaners going boom, which is the sound of a small explosion inside of them, because they're pulling in all of this fuel-air ratio that's inside of here into there, running it over top of the brushes, and you get a big pile of flame that comes out of the outside of your vacuum cleaner. Not healthy for you, for the vacuum cleaner, for anybody. What you should do is always start by blowing, expel. That's going to push out any sort of water, fumes, dust, stuff like that. Push it out the other end. Make sure whoever you're working with knows that you're going to go and blow the conduit out first so they don't get drenched when you push all the water out over top of them. But push the water out first. Then after that, once you push that, you can go and pull through. You should have safe air. These are the mice. You can buy commercial ones. You can go and make your own as well. They're really easy to go and make. Sometimes what we will do is we will go and pull these things in. Note how they got a string line on either side of these things. So you can go and put them in ahead as well. Sometimes we will actually put them on to go and clean a conduit out to go and size it. Then we have another one called a mandrel, or sometimes spelled mandrel. And what those are designed to be is they're rigid ones that look like this. They make sure that the conduit is sized, that's not collapsed. If you've got a mandrel, you're going to pull that thing in and you're going to make sure the conduit has not been collapsed. But these ones here are going to be soft. We just pull these things in to get them on, to get a conductor through. Usually then we will take that string and we'll pull in a heavy rope. And then once we've got the heavy rope, we can then go and connect it to our tugger to go and pull it through, or just pull it through by hand itself. If you've ever worked with the tugger, this drum over here rotates really, really slow. And what we're going to do is, if this is where my conduit is, we'll just place that right over here. What I'll do is I'll have my rope from that's going to come up, and I'm going to loop it around here, and then I'm going to loop it back over the top. And that allows me to pull. Whenever I pull, that pulls it tight around the drum, and then the drum, with all of its torque, is going to be able to go and pull that thing. Sometimes you'll have to stick 1 or 2 wraps around that thing, but every time that you go and pull it taut, it assists you inside of that. Okay, that's it for fun pictures that we have. Let's talk about all the rest of the stuff that we still have inside of here. Parallel runs and temperature during installation, splicing, termination, raceways, mechanical protection, etc. Parallel runs are going to be listed inside of our code, inside of section 12, because it's an installation method where we can go and take, instead of having one giant conductor to drag in, we sometimes will go and pull in multiple smaller conductors. Those smaller conductors are going to be easier for us to work with and easier for us to go and terminate. So if I take a look all the way down here, this rule over here, 12.108, gives me a bunch of rules for my parallel conductors. Specifically, what you should know is that ungrounded and grounded circuit conductors in sizes 1/0 and larger. Okay, it has to be 1/0. If it doesn't have the slash rating, it is not good to be parallel. So it needs to be at least 1/0. It cannot be a number 1. We're allowed to go and parallel them, but they have to be the same circular mill type, the same type of insulation, the same manner, the same conductor material, and the exact same length, and no splices through. That just, all of this ensures that they have got the exact same resistance, the same type of insulation. Make sure that they have the same type of XC, because that insulation acts as a dielectric. It will act like a small little cap on our system itself. So make sure that you're following this whenever you are paralleling your conductors. Temperature during installation, we talked about that the last one. Once again, cold weather installation. Do not install anything below 10 degrees unless it is rated as being so. That's out of your Appendix B that you are going to go and find those rules there. Splicing and termination is another specialized set of rules that we are going to go and see. This is going to go and talk about conductors and how we go and join them together. 12.1.1.12 over here talks about just general joints and splices inside of them that we can join with splicing devices, lugs, brazing, welding, soldering, etc. And then soldered splices have to first be joined. They have to be mechanically secure before we go and solder them together. And then the joints of the splice have to be insulated as well. And all joints in splices and conductors and cables have to be accessible. You're not allowed to just go and bury these things all over the place. That being said, you are allowed to bury splices underground in underground runs of cable, but only, and highlight this, if required due to damage to the original installation. What you're not allowed to do is go to your shop and, you know, you've got that whole set of like leftover chunks from other ones. Be like, hey, I've got a 6-meter piece over here, another 4-meter piece, another 8-meter piece. I will just splice these all together underground. You're asking for trouble. Just don't do it. That's a crazy thing to try to do. You're only allowed to splice underground if somebody has dug into that one. When we are in the class, ask me for that one video of a dug into splice. It's just a fantastic, fantastic video. If I am going to go and splice, I am allowed to go and splice them underground with a direct burial kit, or I'm allowed to go and bring the ends up to 1 meter above grade and then stick it onto a little stub pole. You know, bring it up, splice it, and then allow that thing to go underground. Obviously, if you're going to go and do the stub pole, you are going to lose some conductor length. So if I've got a cable that's going underground like that, and then somebody digs into it like that, there's a chance that you might have enough length still over there that you can go and splice those together end to end. You know, if you expose a bit of cable and you can straighten that thing out. But usually what you're going to end up having to do is take out a whole section, a chunk like this, push some up and some. Okay. If we take a look at the 1.1.12, that one's going to deal with, you know, when we're doing general splices. We do also have capping of conductors. That's going to be covered over here in 1.1.4, where we have got unused conductors. They have to be insulated in the same manner prescribed for joints and splices. In other words, they have to go and have the same thing we'd use in a splice, which is going to be moret or an equivalent amount of insulation, not necessarily just wrapping them in tape. Termination of conductors, how they actually connect onto something to power it up, is different than the splices and joints. Joints and splices talks about where I'm going from conductor to conductor. Termination talks about where I'm now going onto an actual piece of equipment. It shall be made by means of pressure connectors, solder lugs, or splices onto flexible leads. Some types of equipment have got little leads coming off them. I want to think about like dimmer switches, right? We got those flexible leads coming off of them. Other ones have got pressure connectors. That's going to be your screw terminals that you are going to have on the side of a receptacle. And then others could go and have solder lugs. We don't have a lot of those. Anytime that there is a stranded conductor that is being held by the screws, all the conductors all the strands shall be confined, so there's no stray strands to cause either short circuits or grounds. Also to make sure we can get the full current through. And anytime that we've got stranded and solid conductors, 10 and smaller, so 10, 12, and 14, we're allowed to go and connect them by means of a binding screw terminals or studs and nuts that have upturned lugs or equivalent. But anything that is larger than number 10 has to be in a solderless conductor connector, so that's going to be inside of a lug, or has to be soldered into place. So 10 and smaller, we can wrap around something. Number 8, can't do it. Number 6, can't do it. Only 10 and smaller can be wrapped around. There's more precautions than for aluminum conductors because we know that aluminum has got its own issues as well, right? The cold flow that we are going to go and have, the electrolysis, and the oxidization. So when I'm going to go and start them, I have to remove the insulation, any separators. Separators are sometimes pieces of like rope-ish type stuff that are in between. I then need to clean or wire brush my conductors. And then I need to have a joint compound capable of penetrating the oxide film and preventing its reforming. Has to be used for terminating splicing all sizes of stranded aluminum conductors, unless the termination or splice is marked for use without compound. And any time that the equipment is connected to aluminum, it shall be marked for the purpose. The reason for this is the electrolysis, so it does not go and corrode the aluminum. Except where the equipment only has leads for connection to the supply and the equipment such as outlet boxes that have only got grounding terminals. And last of all, aluminum conductors shall not be terminated or spliced in wet locations. Those are all going to be in your Category 1, Category 2, so found in Section 22, unless the termination or splice is adequately protected against any sort of corrosion that we're going to have. Note that the name over here, penetrating the oxide film, our two main names that we have are going to go and be Penetrox and Noalox. No aluminum oxidation, penetrate the oxide. Both of the names are just built around what these things are supposed to go and do. Not that it means anything much to us, I just have always found that little fact to be somewhat interesting. Okay, we are going to go and leave off at this point on this video. We're going to go and take a look at our raceways in another video here.